Welcome to a new test and teardown video. Oh, I feel I'm playing with power supplies all the time. So that is also a lot of fun. This one is an Elektro Automatik EA PS 7016-20 amps. It's quite old, this model. I got the schematic, and I can see inside the schematic on the different pages. We got 91, 94, 97, 98, and even 2002 revisions and changes on the different pages. So they've been working with this quite some years. So that means it is more than 20 years old. It could actually also be 30 years old, this one. It's hard to tell. And it is, of course, obsolete. You can't buy this model anywhere, not from new, not even from used. At the moment, I don't find anything that looks exactly like this. I saw a few of the metered ones on eBay and on some of the marketplaces. They're more or less beat up and looks like I don't know what, and they want 300 or 400 euros for them. So that is not going to happen. This is a very, very nice linear power supply. So I expect we're gonna play a little bit and have a little bit of fun with that one. Today, if you go to Elektro Automatik webpage and look for power supplies, you will see the new 8000 series. It's more or less the same kind of size and idea, just facelifted with new sexy displays and all that kind of stuff. Maybe some of the business and the linear stuff is still the same. I would expect that to be more or less the same. There's no need to invent a lot of new stuff when what you got works. So while I was looking around on the web pages and in the manuals and stuff like that, I find some bugs. As you can see here, they are called -20 amp, but in the manual it shows up as 200A. And if you scroll to the next page, it is correctly made in the same PDF file. Why do we have these kind of bugs? I don't understand that. Let's have a quick look at the back. We see two big fans, and they also got a fan speed control that is controlled by temperature. And on the sticker here, we see the full order code and all that. But look at that, 2001. So I think this one is the latest model. So that is great. Oh yeah, it's 14.2 kilos, and it can give constantly 320 watts. So let's play with this wonderful EA power supply. I don't know if you can hear this, but it's using 41 watts. And it is responding to voltage. Wow, man, there's definitely something wrong. It is not supposed to. 41, yeah. No way. This is not good. Just to show you how you open this case, the 4 screws out here at the sides. This is how you attack this. Of course you don't go to the screws that holds the fans, all right? And then you just pull out this back, and they have made nice length of the cables like that. So you can have it here, and then you just slide out the top. Oops, there's a cable. So of course I got my thermal camera. I'm sorry about that. So I just turned it on again, and then I'm checking for stuff that gets warm. And down here we see some power resistors down there that gets very warm very, very fast. So now we'll look and see if I can figure out the schematic. Got some regulators that gets warm here. That will be for the display, probably because of the backlight here. But there is something. Look at that big transformer, and you can hear it's really working hard. So the 40 watts that we see here, I want to try and disconnect the output and see if it's actually in the transformer itself. Because look at that, I see all the corners here gets warm. And this is where we have the screws, as you can see here, right? So I think they have made a shorted turn somehow using this piece of metal and those screws. I mean, wouldn't you say this looks really weird? What the heck is going on here? This is not how it's supposed to look, right? I have never seen anything like this before, by the way. And we don't see it down there. We only see it here at the top. So what's going on? I have now removed the screw entirely. So maybe this is a part of a short circuit that is going on. My idle power dropped to 30 watts. Of course, it's the whole transformer that is now warm because of all my experiments. But now I don't see those corners warm up immediately. Now we'll let it run for a little while and see if this is normal. So far, so good. Yeah, I still see some. Yeah, that is that. Oh, there's also another little thingy down there that just climbs and climbs. What is that? A little... Ooh, it's a little capacitor or something. Let me get my macro. But I will go and experiment a little bit with this, and then I will do a little bit more documentation. 90 Celsius. Ugh. And I actually did disconnect the high power to the rest, so it can't make anything. So this is all the drive goodies here. I've disconnected the entry to the big bad mains transformer, and now my idle power is 13, and before it was 30. So what is 18 watts of idle for this size of a transformer alone, and it is 500. So that is within normal and expected. And also I don't see any of those red glowing warm screws or anything. So I think we are back to good with that one. So far so good. So now I have 12 watts going in whatever kind of stuff that I wanted to see if that is normal. Now I'm trying to get the hum away, but first I wanted to test the transformer in a standalone situation here. I just put it on a table and a sock under it here, right? So let's try and power it up. It is using, of course, the 18 watts that we talked about. I also measured the secondary. But listen, you can hardly hear it, right? You can imagine what happens when it goes in here. This is like a guitar. It amplifies vibrations, but there is of course some sort of vibrations in this one. So let's try and put this on the table without the sock. Oh, damn, it's heavy. I don't want to drop it. That did not This I can accept. So here's what I want to try and do. I've removed the bracket that holds the transformer, and my idea is that I will try and put some rubber underneath so that the transformer can't really vibrate and get amplified. I also think that if I put some rubber underneath here, this one can't transform to that as well. And I don't want to create a good electrical circuit, because we've already seen that a good electrical circuit to that makes a short somehow. So that's why I'm putting heat shrink here. And what they have already done is they were using some isolated washers like this under the screws here at the front. So they did not want good electrical connection. So let's see if I can make all this happen. So that went pretty well. Look, now we got a thin rubber piece between the transformer, and I was able to find those rubber feet, the sticky rubber feet. They were on this sticky, and they were tiny little, and I cut them and glued two of them on top of each other, and I placed them right next to the hole where the screw goes underneath the transformer, and that made the transformer height from the back plate here, right? So that the screw goes straight through the hole and through the transformer directly without lifting, or there's no weight now in the screw. And of course I also isolated the screw, so it's standing completely in rubber, and all this is going to be perfectly fine. Oh yeah, by the way, did I show you this? It's also written 2001 on the transformer. So yeah, clearly this unit is from 2001. But let's try and power it up again. I don't know if you can hear this, but I cannot hear anything at all. You can hear the fans. So where's the hum? Man, it's gone. Now it is silent. I love it. Now we can get back to business. Now we can start playing with this thing. Meanwhile, before we play, maybe we should look a little bit at what else we find in this fantastic box, right? So those tiny little heat sinks, as you see here, they live only by the air from the fan, and then we have holes in the lid here at the front, so the air is pressed directly through the fins like that, right? If you look carefully here, I think, yes, I am able to show you this. They intentionally put some sort of a little washer down there, so there is no thermal transfer from the heatsink to the outer aluminium bracket here. And this is really thick and stable, and look at the size of that thing in the whole length. It even connects to the rear plate and everything, and it's the same at the other side. Here is the rectifier, and they've done exactly the same. So they want the internal heat sinks to be able to just skyrocket temperature, and then the power supply is still going to feel nice and cold on the outside. When the user touches this, oh, this is not that bad, it's not warm or anything, but it's probably red glowing warm on those tiny little power supply. Well, I of course don't know how hot it's going to be yet, but I am going to play with this. But I can tell you another little trickety trick here they have done. The rectifier. Let's zoom in on the schematic and see what they have done here. The rectifier, they have done an active SCR rectifier. So they're probably pre-regulating the DC voltage on the capacitor system that you see here. All those big capacitors, so they're pre-regulated. So there's not more voltage here than you need. And then the last few volts will be dissipated in the linear regulators. Also, this power supply comes in many different versions, many different voltages and currents and whatnot. As you can see here, we can mount another transformer, and they can also be deeper, and they can be for much more amps, many more amps, and then you can plug in a few more transistors. This one got 4 out of 6 mounted. I think it's a little bit funny that they choose to have the 4 closest to each other instead of having 3 or 2 here and 2. I don't know. They could have separated them. That will be a lot better when it comes to thermal. Also, what I've been investigating in, this is R25. This one goes burning hot. This one is a bleeder resistor that is just in parallel with all the capacitors. So this is what discharges the capacitors when you go up and down in your voltages. So the pre-regulator can do its thing. Depending on if you have no load on the output, of course, then this is the one that discharges the capacitors. Those two also gets burning hot. And I don't know if that is easy to see, but that is R35 and R36. They are the minimum speed for the fans. This is what they do. If we see the schematic here, you can easily see that the transistor shorts, or it can short the resistors, and then it can crank up the heat when this heatsink gets too warm. Those two black wires here, they are from an NTC resistor, and that NTC resistor goes to this system with a little op amp here. And this is just an LM258, and those parts here, they're doing the fan regulator. Even the banana plugs, they're a little bit special because this is high current, and a normal banana plug you put in here, it can't really handle all that amps. So this is 20 amp, but you can also get them in 30 and 40 amps, right? So as you see here, you pull out and then you get access to the screw. So you can screw it in, and then you can see here we go. I think that is a little bit odd that it's not going in or out. So when you screw it like that, you can't see what's happening. A little bit funny, huh? So I think it is time to play a little bit with what kind of current this thing can do. Ooh, there's something wrong with this potentiometer here. This I need to handle. I have to crank up the voltage, and this way I was hoping to get 16 volts out, because that is needed to get the 320 watts out, which is the maximum potential of this unit. Could be interesting to see what is going on. So let's just give it some amps, only 5 amps. Okay, and that meter is accurate. So far, so good. How about we give it 10? So 10 amp, this is quite easy, right? So it is 158 watts of output power. The input power is 289 watts. And if I'm not mistaken, I hear some funny sounds from my load. That can't be good. Is that supposed to sound like that? Is it going to blow up in a second? Why are you sounding like that? See? So this is the load, and it's only doing 10 amps. It was supposed to be able to give many more amps, but it sounds like it's getting angry at me. I think the fuse is gonna blow soon. So this is 15 amps, right? And I am now pulling 390, but I think I put a 2.5 amp fuse in my variac, so it's probably gonna pop in a minute. So what is getting warm here? This is the rectifier side to the left. This is the linear regulators to the right. That'll be the emitter resistors that we see here. And the transistors. I really like to see that all of them, they are exactly the same temperature. All that tells me that we are great and good and happy. Even the wires to the transformer gets nice and warm. And as you see now, we don't have those funny hot spots in the corners of the transformer, and everything is perfectly fine with the transformer. I smell something weird, so I'm probably gonna turn it off right now. I need to investigate a little bit more what's going on here. So that is the rectifier we see down here. It's nice and warm. And now the fan starts to speed up here. Nice, nice. I think this backs up exactly what I said about the whole side here of the whole case. I don't know if you can see that, but it is ice cold, right? At least compared to the heatsink in here. And there is no thermal connection between those two. That is a big, big design fault, if you ask me. But I don't really see anything getting alarming warm or anything here that is bad. Of course, this design, you need the case here, otherwise the air is not going straight through the heat sinks as it was designed for. And I do believe this brand of power supplies, they are designed for serious lab experiments and such, so you should be able to load them 100% 24 hours. And that is definitely what you should be able to do. I don't know if I dare to repeat that experiment, but it should be able to do that. Oh, bummer. So this is why this potentiometer was all the way out and looking real bad. And you know what I think is the problem here? This is a classic design thing with this type of potentiometer and this type of knob, by the way. So when you tighten this this screw here, this holder with the 4 fingers actually grabs and pull a little bit. So if you have this all the way in and you tighten this screw, it really pulls with an enormous force on your pin. And when I look at the other, they are mounted all the way to the front, not even a tiny little distance, but somehow they don't. No, they don't touch. So at least that is good. Sometimes you hear this scrape sound, then you know it's real bad. But here it's okay. At least they are just not touching. No, here. There is a little scrapey sound. And I see that it is not going to be that much fun to get that board out, because it is mounted like that. So you can see how easy is it to service this potentiometer, because we need to get everything out here. We got some sockets here, we can unplug all that. I don't know. How easy is that to do? Let's play a little bit with the pre-regulator, how that one works, the SCR rectifier regulator. So this is the voltage on all the charge capacitors. I'm monitoring that. This is of course the output voltage and the output current, right? So I managed to fix this potentiometer here. I just plugged it in and real carefully figured out how to hit that sweet spot, and it felt a little bit like click, but I don't dare to pull it now, but at least it is in and it stops the right places and all that is fine. So now I've put on my load again and set it for 10 amps just to see what happens. So I can pull 10 amps at 1 volt if I want to, and then we have only 8 volt on the pre-regulator. We can also see how much ripple we got here, only about a half a volt. So 8 volts and 10 amp. So this is 80 watts in this tiny little heatsink. So of course it's gonna be real warm and all that. But for this experiment, I don't think okay, let's just change the current setting on the load, because I don't think that is the problem or the challenge for the pre-regulator. See, it's more or less the same. So that is my 1 volt, 1 amp output. And let's play with the voltage. See, it's just constantly trying to give me 10 volts pre-regulated. Let me crank it all the way up to my maximum output. See, I'm still a little bit sad about that. I really would like to see 16.0. So hopefully I can find a little secret trimmer to fix that. But yes, definitely the pre-regulator tries to give me 10 volts. But again, 10 volts times 20 amps. So that is 200 watts. It is intentionally trying to dissipate into the heatsink. All you have to do is lower that pre-regulated voltage to 5 volts, and then it's only going to be 100 watts. It is that simple. But of course it is also a ripple kind of thing. So let's try and play with ripple. So let's just go for 5 volts, right? And then let's look at the pre-regulated ripple. That is only 1 amp. Let's crank it up to, so that was 10 and a half. Okay, let's try 20. So now we see a little bit of, so this is my 20 amp. Okay, so it can, no, it is in constant current mode. So it cannot do 20. Yips. That is 19.9 on my load, but here it says 20. So this is its full current. Okay. So I think I am getting to the bottom of this thing. Look at that. Now we can give 16 volts. I always want just a quarter or half a volt over the max, because you just want that. So now I feel a little bit happier. That was easy to figure out, because there is a trimmer down there that is called U max. The fun thing is they glued the trimmer So it was real hard to get moving. But you know what? It goes the wrong way. So when you turn this down, you get higher output voltage. And we also have a problem with the current. At maximum with both of these, my output current goes into limit at 19.9. And in that case, I want 20.1 or something like that. So there is another one called I max down there. But you need to be some sort of a magician to access this trimmer, because it's underneath that flat cable. And there are just so many things to complain about when it comes to those little small dummies that doing this thermal thing. I cannot get over it. And the schematic, I mean, did I show you the schematic? Let me just one more time get it out. Let's just rant about this for a minute, and then I will feel a little bit better afterwards. Look at that schematic. There's just no way this is done by a real engineer or anybody with a brain. It is just the most useless schematic I have ever seen. There are just a gazillion things wrong about this. It's impossible to read, and the way that they've drawn all the ICs, and there are no indication whatsoever what each IC is, what it's doing, no text around any trimmers or anything what it is doing. And also all the connectors, they are called all this X this and X that, and if you go to another schematic, you see it's called something completely different. So figuring out how stuff is connected, oh man, it is impossible. They don't want you to understand this or figuring anything out, and it's just, what the heck did they do here with that schematic? It is so uselessly bad. So here you go. Now the amp meter is also accurate. I just like meters to be as accurate as they can be. It was reading 2% too much. They saved the trimmers. This is the voltmeter and amp meter power supply, and here there's like supposed to be a trimmer for amp readout, and here's supposed to be a trimmer right there for the volt readout. And they put in, so you could easily put in resistors here and test this, and it's probably better, more accurate to have a fixed resistor like that. It's much better quality. So of course I'm also doing that. It was a 10 ohm resistor, and I had to put in a 470 on top of that one to make the ammeter accurate. So let's try and crank up the current now and see, are we happy now? 20. And it can do 20. I am super happy about that. I did of course make it so it could do a little bit itsy bitsy, like, oh, now it can do 21. That is not good. Yeah, okay, here we go. Okay, it can do 21 then. So it is. You get an extra amp for free. After I posted some pictures in a local group, some thermal pictures and the pictures of the transformer with the very hot 4 points of the screws, and I came with all the text about, yes, when I released one of the screws and all those heat up points went away. And then everybody starts to think they know exactly why is this going on. And it's not exactly obvious what is going on. Because if you have the normal windings, they are in here in the middle. So this is one winding. The yellow wire here is just one turn. This will tell you how much is this core magnetized. So what is the field per winding, right? So let's have a look at the yellow one turn. So that is 940 millivolts per turn. That is very, very high. And of course the field goes up here in the iron core, and then it goes to the left and to the right. But it should be exactly half of it that goes to the left and to the right, because all the dimensions here is completely symmetric, right? So that means if you take a turn here, you should expect the fields in this area here to be absolutely zero. And some of the guys got a theory that says this very powerful field in the middle actually escape here and is not going that way and that way. So that means you have a winding here, if that is the case. And this is what we're going to find out. So now I'm measuring the blue wire, and let's turn it on. Ooh, that is interesting. 0.3 volts in the blue wire. And the blue wire goes around here. And it should have been 0. So there's a field that escapes here. So of course there's a winding here if you have an electrical connection here. Of course it is not a winding like a real winding down here where it gives you 0.94 volts, but it gives you definitely some voltage per turn. And you can imagine screws made this big and thick like this will be able to carry a very, very high current at a very low voltage. And on top of that, what they have done on this particular transformer, they have used this type of washer, and that gives you a very good contact because it will dig its way down through the material. So they've just taken the wrong washers. And if you go and look on the internet, or you go and look at all the different transformers you have of this type, you will find little plastic washers. And you will find that they are trying to isolate this loop. So the screws and the mounting, the metal and all the parts around here is not creating a shorted winding. I wasn't really happy about this dangling around without the screws. So I 3D printed some washers and some spacers in PETG. So this handles quite a lot of heat and is very, very strong and super easy to make. And it takes only a few minutes to 3D print exactly what you want. And as you can see here, this is nice and fine. So I'm quite happy about this solution. They really tried to create electrical isolation here. You can see those little plastic isolators on both sides. And that is a little bit funny because all the transistors, they are actually isolated, and there's also the overvoltage protection SCR is also isolated from the heatsink. I even tried to scratch a tiny little hole here and a little hole here and do some isolation measurements, and yes, it is completely isolated, and it's the same over here. Nothing is electrically connected to the heatsink or the chassis of the circuits, but still they added extra electrical isolation, but that also adds thermal isolation. They even have this a little bit less than 1 millimeter distance at the top and about 2 millimeters at the bottom. So what I want to try and do is add some gap pad. So this is some very, very heavy, very funny and special material, and it transfers heat very, very well. So if I could stick this down here and screw the heatsink back on, if I can transfer a lot of the heat to the side, then my heatsink here will run a lot colder. Remember, this is 200 watts in this heatsink at full output power. So I'm done installing gap pad in the linear regulator section here. I didn't do it at the rectifier because that was running a lot colder. I let the power supply run at full current for a little while, and I don't know if you can remember earlier in the video when I loaded the power supply. Of course, this is the temperature of the emitter resistors, and they do go very warm, and this is 126 Celsius, and this is of course alright, they can easily handle this. But I don't know if you can remember how hot the heatsink went immediately. But as you see now, there's a big difference. Now the heatsink is pretty much cold. Of course, it's all about auto scaling, as you can see here, right? In this view, the heatsink appeared to be cold. But once I go over here where we only see the heatsink, it of course appeared to be warm. It will scale everything to the minimum and maximum. But let's look at the temperature differences. So we see 38 Celsius on the end, and we see 29 here. It's getting a little bit warm down here. 40 and 35. So the gap pad is doing some sort of magic to the case. Oh, this is really annoying with the shiny screen here. See, this is the side of the screen is now getting a little bit warm. But this will allow you to run this power supply at much higher currents for much longer time. And first now the fan starts to go up a little bit. Nice. That is a good fix. I think I'll do that to the rectifier side as well. But I mean, it's not really needed. It's not a lot of heat in the rectifier side.